Welcome back to Lab 1, Building a Coin Flip Universe, Part 2 of 5. In Part 1, we framed the lab and learned the rules of reproducibility. Now we build the coin universe with a known parameter, draw from it, and reconstruct the sampling distribution of the estimator by brute force, watching it tighten and go normal, exactly as the law of large numbers and the central limit theorem promised. Step 1. Build the universe. Write a function that draws one sample of n Bernoulli p trials and returns the sample proportion p hat, the fraction of heads. The cleanest way is Rng.binomial with n equals 1, probability p, size n, which returns an array of zeros and ones. Their mean is p hat. Because you set p yourself, you hold the ground truth the rest of the lab is graded against. Here is what to expect. With p equal to 1/2, a single p hat from 10 flips might be 0.3 or 0.7, wildly off. At 100 flips, it sits within a few hundredths. At 10,000 flips, it pins 1/2 to 2 or 3 decimals. You are watching the law of large numbers in one line. P hat converges to p as n grows. The estimator is consistent for the true proportion. Step 2. See the distribution. One p hat is a dot. To see its distribution, repeat the draw thousands of times and histogram the results for several sample sizes overlaid. You are reconstructing by brute force the sampling distribution Chapter 1.3 defined and 1.4 gave a shape to. Two facts you will verify, not assume. First, it tightens like 1 over the square root of n. Theory says the variance of p hat equals p times 1 minus p divided by n, so the standard deviation across samples is the square root of that. That is the standard error of a proportion. Quadruple n and the spread halves. Second, it goes normal. A proportion is just a mean of 0, 1 draws, so the central limit theorem applies directly, and you watch the bell appear. Standardize each p hat, subtract p, divide by the theoretical standard error, and overlay the standard normal. There is one subtlety worth chasing. At small n, the histogram of p hat is visibly lumpy. With 10 flips, p hat can only be 0, 0.1, 0.2, and so on, 11 discrete spikes. And if p is near 0 or 1, it is also skewed. It cannot go below 0 or above 1, so one tail is squashed. The central limit theorem still wins as n grows, but it arrives slower, the closer p is to an edge. Try p equal to 0.05 with n equal to 30, and you will see a clearly non-normal pileup. The n at least 30 folk rule quietly assumed a p not too near the boundary. A common practitioner's check is whether n times p and n times 1 minus p are both at least about 10. You computed the standard error two ways, empirically and from the formula. And they agree because they measure the same thing. To summarize Part 2, the sampling distribution of p hat centers on p, tightens like 1 over the square root of n, and goes normal, the law of large numbers and central limit theorem made visible, not asserted. But the bell arrives slowly near an edge, when p is close to 0 or 1, so check that n times p and n times 1 minus p both exceed about 10. In Part 3, we stop describing and start deciding. We write a one proportion test from scratch and then measure whether it really fires at the rate it claims.